Thank you, Arnaud, for the nice introduction. I'll be telling you a bit about this work that we did in collaboration with some people at IFISC at the IPC in San Sebastian. It's about the role of coherence in reservoir computing, and to make it a bit more catch the attention of the people in this conference, I always highlight that it's on the transverse-field Ising model, so that there's also something you can hold on to. So let's get right on it. Okay. We should start first with an introduction to quantum reservoir computing. So we should first start with an introduction to reservoir computing, the classical version of the thing. So this is just a supervised machine learning algorithm, well, a paradigm, let's say. You can do many algorithms within this paradigm. And you may have heard it, if you've been in the field for a while, also as echo state networks or liquid state machines. This is like how it began to be called when it was proposed in the 2000s or so. But then, yeah, this reservoir terminology was adapted. And essentially, this is a framework that was planned for temporal data processing. So this is relevant in the sense that the objective that people had with this is to make use of the internal memory of what the reservoir is, which I will explain in more detail in a second, to not have to have the memory in an external drive, if you will, but just keep it all within the system that is computing. Okay, so I already said that the purpose of this was temporal series processing. So people thought about this in terms of recurrent neural networks, right? Which is, this is what they do. So here this is like a generic picture. I don't think you see my laser point yet. There you go. Of just a neural network, but think of it as a recurrent neural network. And in the scheme, you have an input, a hidden layer, and then an output layer. And what reservoir computing does is fix the input and hidden layers with some random weights and say, I'm not going to train that. I'm just going to train like the other part. It's too expensive to do the whole thing, which is like nice. I like reservoir computing and quantum reservoir computing because it's like machine learning easy introduction. And the nice thing is that you offload all the nonlinear processing to the fixed part of the reservoir and just worry about training a very simple, efficiently trainable output layer at the end. So yeah, this is the whole scheme in the classical realm. And as I said before, this is what we are going to call the reservoir. So this was originally proposed in the context of artificial neural networks, but people quickly thought about this. Actually, when they talked about liquid state machines for the very first time, I think they were already thinking about neurons. But people quickly thought about, okay, if this is fixed and random and I don't actually need to touch it, I can just have a physical system do this job. So you actually have several classical proposals of reservoir computing, just using waves of water to compute, using optical stuff, of course. Quite a bit using, well, more than I expected, using like the soft bodies of aquatic animals also, which I think is quite fun. And so yeah, I already listed like quite diverse reservoirs. So what does it take to become a reservoir? Do we have any? Yes?
What's the resource that they're extracting from?
So here they would be measuring, they have, well, I haven't read the papers in detail, but they have like sensors on the movement. Like they maybe put an impulse and then this moves, and they record how it's moving.
The point is to get random numbers.
The point is to get a series of measurements that correlate with the time series that you are injecting here, because it's going to move according to the stimulus that you gave it, essentially, and the list of like the ordered sequence of stimulus that you gave it. That's the point. Thank you for the question. Okay, so the conditions are actually very general. Like technically, a rock could be a reservoir. It would just be like a really bad one. Okay, but so the nicely defined mathematical conditions are the echo state property, which was already talked about in the original echo state network paper. This essentially just ensures input separability, so the reservoir needs to depend on your input. Otherwise, you won't be able to do much with it. Right, and this is like the kind of the reservoir map that we're going to. This laser pointer is not very, there we go, you just need patience. The picture that you need to have in mind. So your reservoir depends on the state of the reservoir at the previous time step and of the input data that you introduce at that time step. And then if you extend this to the previous steps, you realize that it has to depend on the previous inputs. Okay, and the other important point is that you do need to remember your past inputs, but you kind of don't want to do this forever and ever because you want to be able to initialize your reservoir in a state that is like agnostic to anything else, because otherwise we'd go crazy, essentially trying to predict different sets of data. All right, small remark before I go into quantum reservoir computing full on. This is because it's like a bit of a confusion that I think has been rising in the field, and it's that the terms reservoir computer and extreme learning machine kind of are used interchangeably, but they're not exactly the same thing. So essentially, reservoir computing implies this thing with using the memory that is within the system. And extreme learning machines do not necessarily do that. So you could have like just a single layer, puts an input, shake it a bit, and then measure outputs, and this would be an extreme learning machine. And so there are some experiments that actually do this extreme learning machine thing, but it's called like reservoir learning. So it's like a bit confusing, but just so that you know the difference. Okay, so let's finally get to the quantum reservoir computing paradigm. It's essentially all the previous stuff, but now we have a quantum physical system in our case, because we're interested in the analog version of this, but you could also put like a quantum circuit here. People have done this, people study this as well. And the point of putting a quantum system here, or what people hope, is that, well, okay, I have like a few qubits here, but my Hilbert space is way larger, so I could spare like a bunch of classical nodes by having a fewer, just few quantum nodes, the exponential dimension of Hilbert space. I'm sure you've heard about this argument before. And the point is that this, the dynamics of this quantum system is essentially going to implement some quantum kernel method onto the input that you inject into it. So the way this is going to go is we're going to have some series of data, and we're going to inject it every time delta t into our physical system, allow it to evolve for this delta t, measure some output observables, but not the full system, just some output, like trace out part of the system, get some information out of that, inject some input, repeat the process, et cetera, for however long your input sequence is, essentially. You can already guess, well, and then take all those measurements, pass them through a linear regression. Remember, this is supervised learning, train it, and get your output. So there are many moving parts here, which is why reservoir computing literature is very diverse. Essentially, you could choose whatever here. You could choose whatever scheme to input here. You could choose whatever observables to measure here. Well, and you can even try to get fancier with this, but that's like something that we're not going to touch on because we kind of explicitly want to exploit that that's a linear regression and that's easy and efficient to train. So within like this whole paradigm, the question that we were interested in answering was, okay, so we talked about this exponential dimension of the Hilbert space, but we all know that just by putting a quantum system doesn't mean that you're exploiting like the full Hilbert space of the thing. So how does the reservoir benefit from being quantum really? That's kind of what we wanted to figure out. And the way that we're going to do this for the particular model that we are studying is we're going to take this quantum reservoir and essentially kick it, try to get the quantumness out of it progressively by introducing noise and the coherence. And we're going to see how the correlations decay and how the performance drops as we do this. And then draw conclusions. Yeah, and also by doing this, we get a tiny bonus, which is some systematic study of whether we will get some improvement on the performance by adding maybe a little bit of noise, which was like a thing that some people were observing on some papers. This, I'm not going to talk about it much because it actually highly depends on your whole scheme. Our scheme is quite dissipative already on the way we introduce our input, so we will not see this at all. But yeah, this is also like a good thing to note. All right. So I said that we're going to track correlations, and we're going to try to do this to track how quantum the reservoirs, or the reservoir state is. But if you've tried to do this for a quantum state at any point in your lives, with a bit of detail, you might have realized that it's not that easy to distill what part of a quantum state is like quantum, super mega quantum, and what part of the correlations could also be described by a classical distribution. So it's like, in my mind, I like to think of it as like some water, and you have some oil, and when this is all mixed, this is like the quantum part, and this is like maybe the classical part, and you would ideally like to do this, but you actually cannot because, for example, coherence, you have some off-diagonal elements which cannot exist in a classical state, but if this coherence is like local within the qubits, just a simple rotation will give you like maybe a classical distribution again. So yeah, you kind of need to choose how you're going to measure this. And there's this nice paper from my collaborators that we took as a reference framework to look into this. So I'm going to talk a bit about the exact measures that we look into. So one of them is coherence, so just like the full off-diagonal elements of our density matrix. We will also be looking into the total correlations of our quantum state. Like this would be the sum of the quantum, the classical part, and the in-between part, essentially. And this is just the relative entropy between our true quantum state, our full density matrix, and what would be like the partial trace, the tensor product of the partial trace of each individual qubit. So like the computationally useless state that is closest to our quantum state. Then, as a sure measure that we only have classical stuff here, we're going to look at the totally classical correlations, which is described here with this K. And this is just the total correlations that are contained in our state after the fully dephasing operation. So if we remove all the off-diagonal elements, we have like a diagonal state now that is potentially could be originally a classical state already, and this also will contain some correlations because classical states also contain correlations. And this is what we're measuring. And actually, to go full circle and be able to do like a nice closing of all of this, we should have looked into the quantum discord, but this is actually very expensive to compute, so we just did the negativity. I'm sorry, it would have been very satisfactory, but we could not do this. For a measure of truly only quantum stuff in here. All right. That was it for the measures of correlations. How did we measure performance? So this we did through this information processing capacity, which was introduced already quite a while ago by Dambre and collaborators. And it's a very nice measure to like see and interpret. It's not a very nice measure to code. I can tell you this from experience, but it actually gives you a lot of information. It's quite nice if you manage to do this, but it is very computationally expensive. So this does provide you with a complete characterization of the reservoir's computational power, if you will, because it's designed precisely for that. So what we do here is take a series of tasks, of prediction tasks. So we're gonna be trying to, each of these tasks is predicting a basis of function space. So we choose the Legendre polynomials basis, which is pretty standard for this. And we are going to, so for the reservoir scheme that I was showing you before, we're going to do this many, many times for all these different tasks. And when I say that you do this basis, it's not just, okay, Legendre polynomial of degree 0, predict that, that's fine. I do Legendre polynomial of degree 0 on my current input, on my input, on my previous time step, on the previous, on the input, on the previous time step, and so on and so forth. So I have to take into account all the delays, all the potential delays that I can introduce in my data that would go through this polynomial, because I also want to evaluate how far back in the past my reservoir remembers. And this, as you can imagine, I just described it a bit over, like just talking for degree 1, but if you have degree 2, you obviously have to consider permutations, you will have to consider windows, okay, like delay 1, delay 2, delay 1, delay 3, etc. This is where the computationally expensive part comes in, unsurprisingly. But actually, there is a correct ordering of doing this, such that you always get decreasing contributions. And this is described already in Danvers' paper. So you just need to sit down, program it, and be done with it. You don't have to look into this code ever again. It's actually on a GitHub repo already. If you want to not even have to worry about this yourselves, you can just use our code that is already developed. OK. And with this technique, you can actually discriminate the degrees of nonlinearity that your reservoir is capable of achieving by just, well, so for each task, you're going to benchmark the performance of how well your reservoir did with just like mean square error, very standard measure. And you're going to add up all these contributions for all the different degrees of all the functions that you are computing. So for degree 2, I will account for the Legendre polynomial of degree 2 plus contributions plus the product of 2 Legendre polynomials of degree 1, et cetera, et cetera. And these are like all the tiny contributions that you see here. This is essentially how we calculate all of this. And you see, well, there's some error threshold, well, some noise threshold that you need to kind of cut off. But this is like numerical details. But yeah, I think this is all I wanted to tell you about this. So I think I'll be moving on. All right. OK, last ingredient of all of this. So I said we were going to be introducing the coherence. And this is essentially how we're going to do it. We assume 2 very standard, very theoretical noise models, just independent noise locally acting on every qubit. And, well, and this is going to be bit flip noise and phase flip noise. And the way that we perform our numerical simulations is by like exact diagonalization in a trotterized manner. So we diagonalize our Hamiltonian, evolve a little bit, and then every like eta steps we apply these this map right here, such that what we're effectively implemented is a trotterized Limplerian. All right. So I promised the transverse-field Ising model. Here you have it. And this is essentially the system that we are going to consider as our reservoir. So we will have these couplings be randomly sampled uniformly between 0 and 1, then some mean value for the local fields, and some randomness that will also be uniformly sampled. So the reason why we leave this like a bit up to chance, well, not up to chance, but up to choice, is because there are different, like already known from previous studies, dynamical regimes for this Hamiltonian that have different performances for quantum reservoir computing. And we also kind of wanted to explore this effect of, role of coherence in this couple of regimes. So we have, well, a way to see this dynamical regimes that link to performance as well is through this average adjacent gap ratio. You don't really need to care about it much, but I'm sure it rings a bell for many of you. And essentially here we can identify like a many-body localized phase and an ergodic phase, and essentially performance is typically better in the ergodic phase versus the many-body localized phase. There's some results that I'm always involved with that actually argue that it's not really about the dynamical regime, it's about the localization. In this case, for us, they are the same thing, so you don't need to worry about it. But yeah, so we will be looking into these two regimes. Well, as a fun fact, because we were looking into this also with the coherence, we found out that the coherence alone, just looking at the coherence, it tells you the dynamical regime that you're in, which we thought was cool. And these are the 2 points that we're going to be taking as the representatives of each dynamical regime. So just like very large disorder on the local fields for many-body localized and 0 disorder in the local fields for the ergodic part. All right, almost done with the ingredients to all of this. So the last moving part that I need to describe is how we inject our input into the reservoir. I kind of need some water. I'm very sorry. I swear I did drink before the start of this presentation. All right. Sorry about that. So yeah, the full reservoir map is defined also with the, by the input injection scheme. So here it is. This is essentially the scheme that was originally proposed by Nakajima and Fuji in this paper in 2017. It's, thank you, not necessarily the most experimentally friendly, but it's the one that we went with because it was already there. But actually, we were looking into other input injection schemes. I will talk about, a bit about this at the very end also. But essentially, at every delta t, we prepare the input qubit, which is always the same, Jesus Christ, in this state, according to our normalized input, and just plug it into the rest of the system, let it evolve for delta t, do this over and over. But you can see that here, since we are tracing out this qubit, we are already introducing quite a bit of dissipation, which is why in our particular scheme, adding more dissipation is not going to improve at any point. All right, so here's the full thing that we are doing. So this is our spin system. It's going to be a fully connected 5-qubit network, 5 because we are doing a lot of decoherence simulations. So we could not go further for that, than that with our computational resources. And we are going to be averaging over 10 random realizations of the system and the results that you're going to be seeing later. This is our input injection qubit. This represents like the noise that is happening around here. Jesus Christ. And we're going to be measuring, as I said before, after every delta t. We're going to be collecting some observables. And importantly, we're going to be applying some Gaussian randomness to them to simulate the shot noise that you would get from a real experiment. And we actually observe, as I will comment later, that this can change the interpretation of the results if you don't actually do it. So once we have this smoothened observables, we can train our weights and do our IPC calculations. All right. So what did we actually observe? It's okay. I'm okay with water. Thank you very much.
Sure.
Yeah. Otherwise, I will it will stick to my throat. Okay. So with respect to the correlations, we see actually already quite a different behavior between the ergodic regime and the many-body localized regime, as would be expected, because I mean, we already knew that they would have different dynamics. But interestingly, especially you can see that in the MBL regime, the phase flip noise is not impacting the performance, the correlations, the totally classical correlations as much, which kind of indicates that there's quite a bit of information in the totally classical correlations to begin with. Whilst in the ergodic regime, they both decay more or less following the same curve, which means that information is not completely contained along this axis, and it's the same thing for the total correlations, which is the mutual information, by the way. They're the same thing. And yeah, kind of everything we need to say here. We will take this, do other things with this data later. As per the performance itself, okay, there seems to be like a lot of information here, but you just need to take into account that the left bars are the bit flip noise, right bars are phase flip noise. And you see that we looked into different observable sets. So this would be a set with like 10 output functions, all the possible 2-qubit correlations of the set type. This would have 15 observables, all the sets plus the single sets. And this is quite larger. But you can see that they're all normalized. This is because IPC is normalized by the number of output functions. But that's why you see like different nonlinearities that you can observe, because like we're doing more powerful calculations with this bottom plot here, because we are extracting more information from the system. So here we kind of observe like a similar behavior and a similar difference between the MBL phase and the ergodic phase. You see that they have like different observables, but we put them because they actually showed very similar results, and the set I need some more water. Looked very similar also. So they all showed very similar trends. All right. And you can see, again, that, I mean, as would be expected, the bit flip noise impacts performance quite harshly in both cases. But in the ergodic case, the phase flip noise actually also is impacting performance, as you can see here, and it's also quite close to how bad it is doing for the bit flip. Also note, and this is something that we can see nicely because we are using the IPC, that the noise that is introduced is killing off the nonlinear processing capacity of the reservoir first. So you can see that this guy kind of stays, decays slower than the higher nonlinear processing capacities. And we can see the same thing kind of all over the place. Then, well, for also the larger number of observables, we also have this multiplex ZZZ. This was just a comparison that we wanted to do. This just means that we're only measuring ZZ correlations, but we are measuring them also in between some smaller time intervals while the system is evolving. And we observe that this does essentially equally as well as measuring all of this, which is non-commuting and a pain to measure. So essentially the takeaway here is that it's worth to do this rather than this. All right, so what are our conclusions after doing all of this? So we are just taking the data that I showed you before, the correlations and the performance, and plotting it all together, like one against the other in 2 axes. And well, what I call here I thought this is the height of the full barrier. So essentially from looking at this data, we conclude that the transverse-field Ising reservoir is relying more on superposition than on entanglement for its processing capabilities. Also, as a side note, we also do this analysis for the many-body localized regime. You kind of see the same trend, but the error bars are so bad that we are just going to be talking about the ergodic part all the time. Okay. The error bars are so bad because in the localized regime, the randomness in the couplings that you establish at the very beginning will determine a lot the different performances of this. So this is very variable, while this doesn't happen in the ergodic case. So essentially how we come to this conclusion is that we can see that the negativity can drop quite a bit while the performance essentially remains the same. And the negativity would be linked to what we consider entanglement, while drops in coherence do have like a stronger impact in the total information processing capacity. All right, the other result that comes from our findings is this thing that I mentioned briefly before, that if you don't take it into account this statistical noise, you may run into wrong results. And this was especially evident in the case of the many-body localized regime. where we realized that, well, for this set, but it would also happen for many other observable sets, if we just looked at this without taking into account the, any kind of smoothing, so we take just the simulation precision, this is the same as accounting for infinite measurement, we would see that indeed the performance improves. So this was like this thing, will the coherence help or not? Well, when we take this into account, it immediately like drops really badly, actually. And we were wondering why this is, and we thought about, okay, let's maybe plot some observables here. And this is just the reservoir map and the evolution of the individual set terms of this. So this is in the non-decoherence case. This is the ergodic like trajectories, and this is the MBL trajectories. And this is in the presence of strong phase flip noise. And we can see very clearly that this strong phase flip noise is actually introducing some data, like input dependence, that was not here in the very beginning. So that's why if you don't consider the fact that this input dependence is actually very tiny, it looks like you are breaking this localization and you are suddenly like processing data. But actually, as I mentioned, this input dependence that you're introducing is very small, and actually you wouldn't see it with regular sampling of your true system. All right. So yeah, this was like up to where we had the paper, but then we had some reviewer back and forth, and this came to like an interesting addition that is in the supplementary material around. So you probably haven't seen this because nobody looks at this supplementary material, I fear. But yeah, it was a nice additional result, so I'm going to tell you about it because I also think I have time for this. Good. Essentially, the question was whether our results generalize for other types of input encoding. So the importance of statistical noise, obviously, yes, because we already saw that this depends on, well, the fact that noise is dampening your signal, and this is going to be like that, period, for whatever system, whatever input injection scheme. But is this conclusion that it is superposition rather than entanglement what is holding our performance going to still be there if we change our input injection? So we're going to focus on the ergodic regime because this is essentially the regime where the reservoir performs well. So this is kind of where you want to focus your studies. So we studied 4 different input injection schemes. This was the original one that we had. We call it mixed in set. We did exactly the analog thing, but on the x direction. So we would now be introducing this information on the coherences. And then we also considered introducing the input through a pure state centered along the z-axis, or doing this in a pure state centered along the x-axis. And you can see some interesting stuff. So let's go through it. Essentially, between mixed in Z and pure in Z, there's not that much difference, but actually pure in Z looks a bit more interesting. You have more nonlinear processing capacity. And, well, I mean, this is like not a lot of points, but you can see also that the saturation comes a bit first. Well, this is actually kind of numerical things, but essentially this higher nonlinear processing capacity is more interesting. And it does, you have to believe me because maybe it's not like super evident here, but it is slightly more robust to noise. And this is essentially because in this input map, we are not dissipating as much as in this one. So we are adding, on top of the coherence that we had, due to the input map, this is slightly less as a base. So yeah, we do a bit better against noise because there's a part of that decoherence that comes from our own scheme. Now, this is great because this is also like more directly implementable, so good news. But we immediately see that stuff starts to get funky if you center yourself around the x-axis. So I'm going to follow this direction. Well, okay, no, I'm just going to talk about it all. So in the mixed in X scheme, we immediately see that apart from only finding even degrees, which is already kind of funky, we see a performance drop pretty bad. And for the pure center around X, we don't have this performance drop, but we do have only even degrees. So we look a bit into this, and it turns out that this is just because we do have some parity symmetry in our Hamiltonian. So we have the symmetry that is constraining the dynamics if you center yourself along the x direction. So there's a lot more going on around the z direction in this Hamiltonian than along the x direction. And this, we weren't able to show it analytically, sadly, but this essentially is going to be what is causing these degrees to be, even if you're only looking at like homogeneous observables, if you will, because we see that if we consider z plus cross terms, we do recover all degrees. And if we break the symmetry in the Hamiltonian by introducing some small fields in the x direction too, we also recover the full degrees and also the robustness, actually, as you can observe. So this is kind of just a consequence of this is a bad input injection choice for this particular system. And you can also see this if you directly plot the observables for all the different kind of schemes up to 2 local. For the so this is the average values in the stationary state. Look at the scale difference, by the way. So importantly, in the mixed in X encoding, all observables are way more suppressed. Essentially, the system is moving way less. All right. So yeah, with this, we can conclude that our conclusions seem to generalize pretty well to other input injection encodings, as long as you do have some component that will encode along the z direction, which is where information is going to be able to spread out and mix. And yeah, with that, I think I wanted to tell you something else, but I forgot. So I hope it comes up in questions. So yeah, I'd like to finish by thanking my collaborators, and I'm open to questions. Thank you.
Thank you, Anna, for this very nice talk. So we have 5 minutes for questions. I see a question over there.
Hi, so my question sort of had 2 parts. The first part is, you mentioned fading memory as one of the conditions for reservoir computing. So I'm sort of wondering, does the existence of external noise provide that fading memory? And is there the expectation that it's beneficial, or is that purely just a sort of classical thing because computers only have limited memory?
Sorry, can you repeat the last part?
So I'm asking is, sorry, is the idea of fading memory actually useful for computation, or is it just necessary because computers only have limited memory?
No, it is necessary. So imagine, Jesus Christ, I swear, like, sorry. So imagine that you fabricate 2 devices of this type. If you cannot forget anything about these systems, just like the tiniest fabrication difference is going to provide different results, because it will remember that it has been fabricated differently. So this is essentially like the idea of why you actually need to, in the far past, you need to forget it, because you will need to, like, also, you want to maybe use this machine to compute like different things. So you will have to transition between data sets and so on and so forth. This is and then for the first thing, I'm very happy you asked me this because this was what I forgot to mention. Which it was related to dissipation, right?
Well, it was whether just external noise coming into the quantum system is providing that fading memory.
Yes, so there is a paper in which they try to only account for the, because if you're switching to quantum, you in principle have unitary dynamics, right? But this is all linear transformations, actually. So this wouldn't be very useful. You need to introduce some kind of nonlinearity, and you can do this by dissipation. So if there's absolutely nothing, then, or if there's too little, so if you were to only allow the unitary dynamics to be twinkled a bit by the coherence, there's already a study that I can send to you later because I don't have it in my slides, that tries to account for this, like, okay, just with the environmental noise, how good our reservoir is, and it's actually pretty bad. So yeah, maybe if you explicitly increase the coupling to the environment to enhance this, you could, but it would probably have to be a parameter that you can tune, because you don't want this channel to be open all the time, because it will go to hell pretty quickly, the whole computation.
Cool, thank you.
Thank you.
So we have time for one long question or two short ones. Okay. So I see two hands raised.
Thank you for the presentation. I have a question. Because if I understood correctly, your reservoir is with 5. So in a classical reservoir, you definitely have some finite size effects. Is it the case also here, or meaning that I guess that it's computationally expensive, but if you had a reservoir of 100 or 200, would it be better, for example, the error bars, or is it enough with 5 qubits in this case, or spins?
I mean, I would say that the conclusions will still extend, because this is a thing of the eigenstates of this model. And I don't think it will significantly change. Since it's an all-to-all connected network, it's not like there's some boundary there that will show up very obviously, I would say. Definitely larger system sizes will be better coherence, better results. You will maybe be able to study a bit better all this effect on the different nonlinearities of the system as you introduce the noise. This could be interesting, because what's a bit open is, because since you do see the higher order nonlinear correlation information processing capacity to drop at the very beginning, maybe these are more related to entanglement, for example. Remember that at the end we were only looking at the total IPC, but we are no longer looking at the different parts. But we didn't have resolution enough to state anything about this with our small system sizes. So probably larger systems would allow you to look into this with more detail, which would be pretty cool. Yep.
And the last question.
So when you showed the difference between the ergodic phase and the MBL phase, did I understand correctly that you get the wrong results if you do not use shot noise? And okay, so this is the first part of the question. And the second one is if you generally have a quantum many-body system and you want to use it as a reservoir, you may have also different phases, like, I don't know, quantum scars, for instance. Is it known in general which kind of phase provides the best for reservoir? Like, for instance, quantum many-body scars are a potentially viable region.
So I am not super familiar with quantum many-body scars.
It's basically when you have a lot of states, a lot of eigenstates that satisfy the ETH hypothesis, but a few of them that do not thermalize. And this happens, for instance, in Rydberg atoms. And these drive the dynamics for long times. But it's a little bit in between. It's like weak ergodicity breaking rather than hard as in the MBL. But more in general, is there some understanding on which kind of phases provide the best for reservoir, or it's unknown?
So actually, I mean, the intuitive understanding that you can see very fast is that you need your information to mix and travel around the system. So this is why ergodic works definitely better than many-body localization. But actually Arnaud himself was involved in a recent paper where they argue that it's not really the dynamical phase, it's the localization part that matters. Because again, would be what is confining your information and limiting it to spread around the system. So if the weak breaking of ergodicity that many body scars have still allow for information to spread out fairly decently, then you should be good, I would say.
Very well. So thank you very much, Jana, for this nice presentation.